Good morning, Professor.
Good morning. Good morning.
Shall we start, Professor?
Yeah, sure, definitely.
Students, we are entering the second lecture of the day. We have with us Professor Mukesh Doble. He is a professor in the Department of Biotechnology at IIT Madras, Chennai. He has previously worked for 20 years in the Imperial Chemical Industry and General Electric Technology Centers. His area of interest are drug design, biomaterials, bioreactors, and bioremediation. He holds a BTech and MTech degree in chemical engineering from IIT Madras, a PhD from University of Aston, UK, and postdoctoral from University of Cambridge, UK, and Texas A&M, USA. He has authored and co-authored more than 250 technical papers, 8 book chapters, including polymers in marine environment, cyclic beta glucans from microorganisms, production properties and applications, drug design basics and applications, green chemistry and process, biotreatment of industrial effluents, biotransformation and bioprocess, homogeneous catalysts, mechanisms and industrial applications. He has also filed 8 patents to his credit. He is a fellow of Royal Society of Chemistry, London, and a recipient of Cadilla Award for Excellence in Basic Research from Indian Institute of Chemical Engineers and the Dow Professor M.M. Sharma Distinguished Visiting Professorship in Chemical Engineering at Institute of Chemical Technology, Mumbai. He is in the editorial board of the journal Chemical Engineering and Phytomedicine and a member of American and Indian Institute of Chemical Engineers. So with this short introduction, I invite Professor Mukesh to deliver his talk. The floor is yours.
Thank you very much for your kind introduction. Let me also thank the organizers for giving me an opportunity to talk to you. I'll be talking about design of experiments. This is part of my NPTEL Swayam course, where I have a very 8-week course on biostatistics and design of experiments. So in 1 hour, I'll try to cover the best, actually. So this 1 hour will be more like an introduction. If one is interested, you may have to download those videos from that NPTEL course and have a much detailed understanding of this program. Okay, so let me share my screen to start with. Can you all see this?
Yes, Professor.
Okay. So I'm going to give a brief overview on factorial designs, fractional factorial designs, and second order designs. So like I said, it's a vast course. It will take much more than what can be done in 1 hour. You can see my emails. If one is interested, you can always discuss with me later on further details about these factorial designs, actually. So these are some references from which I have taken. So you can take a screenshot of these references also if you are interested on how to go about doing a design. Okay, why do we do these experiments, actually? So you may all know, why do we do experiments? Why do we do? We want to do experiments to identify important variables, okay? Then optimize our product or process, and then also achieve robust performance. You will understand these 2 points, but the third point is robust. So if a process is running, for example, fermentation is running, and there is a small change in temperature or pH, it should not go away somewhere, right? It should be stable, even for small changes in feed or small changes in the pH or temperature. That's called robust. performance actually. So we do experiments to achieve that. So I want to have a very strong process which is running in an industry. Small changes in some of the operating conditions like temperature, pH, amount of carbon or nitrogen, flow rate, RPM will not affect my process and take it to somewhere else. Okay. So I need to achieve all this. That's why we do experiments. It could be an experiment for a chemical engineer process development. It could be a bioprocess experiments. It could be in electrical engineering. Somebody is designing motors. It could be in mechanical, somebody designing valves. So you have many variables and you would like to know what is the effect of these variables on the performance of the particular product. It could be a product, it could be a process. Product means I'm manufacturing a drug. So I want to know how the purity of the drug changes when I change some of the parameters. Okay, that is the product related. Process related means it could be like a fermentation which I am running. How does the fermentation yield changes? Okay, or efficiency changes. So it could be a design, could be for a process or a product. Okay, so there are variables which are called controlled variables, and there are of course uncontrolled variables also. Actually, controlled variables means suppose I am running a reactor. I'm a chemical engineer and a biochemical engineer, so I will be always talking about reactors and fermenters. So please understand that. You can always extend it to your example, your expertise. So I am running a reactor, so I can change temperature, that's in my hand. I can change RPM of the motor, that's in my hand. I can change maybe pH, I can change pressure. So they are called controlled variables. But of course, there are some variables which is not for you to control. The ambient temperature may change, the ambient humidity may change. Humidity and temperature ambient will affect the fermentation, the bacterial growth and so on. So there are uncontrolled variables, there are controlled variables also. And then finally, you would like to develop a mathematical relation between y. Y is your dependent variable, okay, like a yield or impurity level. So that's on the left hand side. Right hand side could be an independent variable, x's. We call it x's, we call it independent variable, like your temperature, pressure, pH, RPM, amount of carbon you are adding, amount of nitrogen you are adding. So you may have many x's here on the right hand side. So you may like to finally develop a mathematical relation between y and the x's. Okay, it could be a linear relation, it could be a non-linear relation, or it could be a multilinear. That means many variables coming into the equation, all showing the dependent variable y. Okay, so ultimately our goal is to get this equation. What's the use of the equation? We can, if I want to know if I change x, how it will affect my y. So I can use that equation for predicting later on actually. That is why ultimately we would like to develop a, it could be a regression. Linear regression, non-linear regression, multilinear regression, or it could be any type of mathematical relation or mathematical operation. So there are many software packages which can help you once you have the data to develop a mathematical relation. So basic steps in design of experiments are, so first you prepare the design. In fact, that's what I'm going to show. Prepare the design, then we go to lab, collect the data, then we analyze the data, and then we may make different statistical tools we analyze. We calculate two sample t-test or chi-square test or ANOVA, whatever be it, we do all those analysis, then regression, and then we derive conclusion. Then we say pH has no effect, or maybe temperature has the highest effect. Amount of catalyst is having the best effect, like that, we make a conclusion, and then we plan accordingly. We give recommendations. Okay, so we have to control temperature very, very effectively, because small change in temperature, my yield is changing. So that is called the recommendation. Okay, design of experiments have been there in many areas, agriculture, defense, even you can see chemical industries, manufacturing, quality control, automotive, even in IT. These design of experiments have come up actually. So chemical process, biochemical processes, aircraft, semiconductors, electrical, electronics, everywhere. you want to improve quality, you want to improve product performance, you want to improve process performance, even services, we can have design of experiments. For example, let's take Swiggy. We all know Swiggy. So the Swiggy delivers in, says, 30 minutes. What are the variables that affect that 30 minutes? What are the controllable variables? What are the uncontrollable variables? So that sort of study we can do actually, and then optimize on the time. Can I address some difficult variables so that I can reduce the time? Okay, that's a service sector. So we can use design of experiments in service sector also. Like Swiggy, like your courier person, okay, because he delivers letters. There are many variables which affect his delivery time. Some are controllable, some are uncontrollable. Okay, so how does each variable affect? So we can do a design of experiment study on that also. We will talk about it actually. Now, when we do experiments, we always have to have a comparison. That's very, very important. Suppose I am developing a drug for blood pressure, BP. Okay, so I am going to test it on some volunteers. So I will always have a placebo. Placebo is something which is not a drug. It could be just a sugar pill or a glucose pill or something. So the volunteer will not know he's getting whether it's a glucose or a glucose pill or a real drug. Okay, that's very, very important. So it compares. So how does the BP look? Only you will know whether I have given the glucose pill or whether I have given a BP pill. So we can make a comparison. The blood pressure of a person, volunteer who has just taken a glucose pill compared to another person who has taken a BP pill. Okay, so the comparison is very important. Okay, then we can even compare. If I have male volunteers, I can have female volunteers. Then I can compare how the same drug affects, how much it reduces in a male volunteer, how much it reduces in a female volunteer. That's comparison. So anytime experiments are always comparison. So there is always a control. Okay, so if I am trying a drug, I will suppose I am trying a. You must have heard in recent pandemic also. So when they try an antiviral drug, they will always compare with somebody who is not given the drug. Okay, or somebody who has not been given the drug 1 week back, and then this week I give the drug and see how the viral load goes down. So there is always comparison. Experiments, you should always have a comparison. Actually, if you are a bio background, you will know we have positive control, negative control. That means there are some experiments done without the drug. Okay, there are some experiments done without the organism. Okay, and so on actually. So we do positive control and negative control. So comparison is always there. Okay, even at home we compare, right? This boy is getting better marks in mathematics when compared to that boy. Okay, that's a comparison actually. So experimental plans always compare. So when I'm introducing a new drug in the market, I want to say this drug performs better than the previous drug in the market. So that's a comparison. Okay, so there is nothing like an absolute. It's always comparison. Replication. Replication means doing it many times. That's very, very important actually, because without replication, we don't know what is the error. There is always error. If I same experiments, I do it 3 times, not because I make a fault, because the equipments or their instruments I use, I add some chemicals into a beaker. So small errors add up to, and it will have some number. So I must know what is the error involved. So if I get a result of say 80% yield, if I do it 3 times, it will never be 80. It could be 81, it could be 79, it could be 80.5, it could be 79.1, like that, always. There will be small variation. We call it statistical variation. So any experiments have to be replicated to get an idea about the error involved. Okay, instrument error, human error, assay error, that is the experimental procedure error. If I do it today and tomorrow, there will be differences because of changes in humidity and ambient temperature. Even when I use a different bottle of chemicals, errors. So always do replication. At least minimum 3, 6 is a good number. In biology, we always do minimum 3. Okay, so if you are measuring certain volunteers, okay, on blood pressure, I will not take results only from one volunteer. I will take 10 volunteers for control. That means 10 people who are not given the drug, or placebo, they are given placebo, and then maybe 10 people who are given the drug. More number of volunteers you have, the error comes down, because if you remember your equation for standard deviation, we used to calculate standard deviation. The number of volunteers term will come in the denominator. So when we have more in the denominator, the error standard deviation also goes down. Of course, in some cases we cannot replicate too much, but always you should have at least 3 repeats. That's very important. Never do experiments just once and make a conclusion. That's totally wrong. Okay, so this is quantifying uncertainty, right? Because like I said, instrument will always have error. Operator person will have some errors. The way we are doing the methodology which we get from literature will have some small errors. So always repeat. Randomization, this is also very important. Otherwise I will have a bias. You should always do a randomized design. For example, the doctor may feel, suppose the doctor is asked to give blood pressure pills and placebo pills to 20 volunteers. So when he sees a person coming in, he may have a bias saying that this person looks like a person who may have blood pressure, and he may give the blood pressure drug. Okay, or if a healthy looking person is entering the room, he may think, okay, he might not have blood pressure, and he may give the placebo to that person. So that is little bit biased. So it should be very randomly done actually. That means doctor maybe close his eyes and pick up one medicine and give it to the person. Okay, or toss a coin. If it head, he will give the real drug to the person who is entering, or he'll give the placebo to the person. Okay, so randomization is very important actually. So we it should remove the bias we have in our mind. So when we look at a healthy looking person, we may think he is healthy, he might not have BP, so we may give him a placebo. So that's called a bias actually. So randomization is extremely important when you do a design actually. So there are random number generators. Computers have random number generators. So you can pick up randomly and then give it to the person actually. So randomization is very important. So randomly selecting volunteers. So we don't, if suppose there are 20 volunteers, we don't select 10 healthy looking person in one side and put 10 not so healthy looking person and then give the drug. That is a biased approach. So when you do randomization, then you can use probability theory, because all the probability theory related to ANOVA, related to normal distribution, T distribution, all the theory believes in randomized data. Once you put a bias, none of these theories work actually. So there is a lot of theory behind when you calculate p-value, or when we calculate ANOVA and we use tables. They are all based on probability theory. So randomization is very important actually. Then blocking or stratification. For example, I am going to do a agricultural experiments. For example, I want to test a new fertilizer. If I'm going to test it, for example, there could be differences in the location where I'm testing. For example, if I'm testing it in Trichy and if I'm testing it in Madurai, the farms may be different, so I may get different results. So I have to block it. That means whatever experiments I do in Trichy and whatever experiments I do in Madurai, I keep them as a group separately. That's what is called blocking, stratification. So you need to understand that there is going to be difference between, okay, like Trichy soil versus Madurai soil. Or if I am doing some studies in summer, and winter, definitely because of the changes in the humidity and ambient temperature, there could be some differences. Okay, so that's called blocking. So I must understand that there will be differences. So whatever experiments, I keep them separately, group them, which I have done, say in summer, and whatever I've done in winter, and then analyze data in two different groups. Okay, so this is what is called blocking, actually. Okay, so many things are very, very important when you plan. Control, replication, randomization, and stratification or blocking, actually. Okay. Okay, so one example. For example, I have 20 males, 20 females, half to be treated with drug, the other half left untreated, or with placebo or old drug. But I can treat only 4 volunteers per day because my hospital is very small. So there are different ways you can approach. Okay, so for example, I do all the controls. So 20 volunteers, Monday 4, Tuesday 4. So all the controls, I say I am doing it on 1 week. Then all the tests, I am doing it on the 2nd week. Okay, this is a very bad design because I'm not done randomization. You notice this. So all the controls, I'm doing it. Okay. So all the control, I'm doing it, and all the females, I'm doing it. Then all the males, I'm doing it on 2nd week, which is a very bad design. Okay, now this is a randomized design. You can see I'm mixing up. I am having a treated people also, male or female also, then control. This is a male. Then I may have a control, a female. Look at this. This is a very random design. Okay, when compared to the previous design, this is completely non-random, which is not desired. Okay, I can also do a blocked design when compared to a random design also. Okay. So another way of blocking is only take the adult people alone. So you take only the adult male, you can do a control and treatment. Then you can do adult female, you can do a control and treatment. Then not only between a drug and control you can test, but we can also test between male and females also. So there are different strategies by which we can randomize as well as doing. Now, what is a factorial design? So suppose I want to test a drug, how it acts on a normal diet. Suppose I'm taking normal diet, and how the drug is acting on a high fat diet. So there are 4 possibilities. No drug, because that's my control. Okay, and drug, then normal diet, high fat diet. So we can have 4 different treatment strategy. So I can have no drug, normal diet. I can have no drug, rich high fat diet. I can have a drug normal diet. I can have drug high fat diet. So you have 4 possibilities. Okay, this is what is called factorial. So this is what is called factorial design. No drug normal diet, no drug high fat diet, drug normal diet, drug high fat diet. So advantage of this is we can study the effect of drug, we can study the effect of diet also. So a factorial design, you have to do 4 experiments. It could be rats or it could be human volunteers. Okay, so you have to do these 4 types of experiments to understand effect of drug as well as effect of diet also, actually. This is called a factorial experiment. Okay, so we could have we could add another factor. So we have 2 factors here. Okay, 2 factors means drug, no drug, that is one set of factor. Diet is another factor. You understand? We could have another factor also, male and female. That is the gender. So you can have 3 factors also if possible. But each factor is at 2 levels. Please understand the terminologies I am using. 2 levels, no drug, or normal diet, high fat diet, male and female. So 2 levels. Here 2 factors. If I put in male and female, that becomes 3 factors. Then how many experiments will be there? There will be 8 experiments. So if I put male and female also, it will become 8 experiments. No drug, normal diet, male, no drug, normal diet, female, like that. Drug, normal diet, male, drug, normal diet, female, and then no drug, high fat diet, male, no drug, high fat diet, female, drug, high fat diet, male, drug, high fat diet, female. So that will be 8 experiments. So 3 factors and 2 levels. In this particular example, 2 factors, 2 levels. So we call it 2 raised to the power 2 design. The bottom 2 represents the levels. The top 2 represents the number of factors. So if I put in male and female, I have 2 factors, one more factor extra. So it will be a 2 raised to the power 3 design. Understand? I will talk about it again later, but this is a 4 experiment. So 2 raised to the power 2, that is 2 raised to the power 2 is 4. If I add male and female, that will become 2 raised to the power 3 design. That means 2 into 2 into 2, 8 experiments. So if I put in male, female also, I have to do 8 experiments. So these are called factorial experiments. 2 levels, drug and no drug, normal diet, high fat diet. 2 factors, one is drug related factor, other is diet related factor. So if I put gender also, male, female will be another factor. So factorial experiments will always be like a 2 raised to the power 2, 2 raised to the power 3, 2 raised to the power 4, and so on. Because here I am talking about only 2 levels. So that's why the bottom 2 is always constant. Actually, you can also have 3 levels also. No drug, drug A, drug B, then that becomes 3 levels. Okay, we will talk more on this factor and levels later, but this is just an introduction to that actually. So factorial design, if I have 2 factors, no drug, normal diet, high. So drug and diet is 2 factors. Levels is no S, no S. So no drug, normal diet, high fat. Okay, so other points when we are planning designs are we should consider unconscious biases. So we always have bias. I am a chemical engineer, means when I do some experiments in chemical engineering, I'll always feel something. If I am using different temperatures, I'll feel some temperatures are too high, maybe my catalyst will get deactivated. If you are a biochemical engineer, you'll feel at 50 degrees centigrade, bacteria might denature. If I change pH, this particular bacteria will not work. So I have bias. So that is always there. So we have to be very careful on that. And you should do experiments without knowing the treatment strategy. That is why they have introduced the concept of placebo, where you don't know whether it is a drug or a sugar pill. So the doctor will not know whether he is giving, so that the bias is gone. Okay. So all these points we need to consider when we are planning experiments, actually. Very, very important. Another thing is, are these representative? For example, I am measuring sugar level in patients. I am selecting 10 people in Chennai and then measuring sugar levels. Is it really representative? Can I tell those 10 people represent Chennai? No, definitely not, right? Because those 10 people may be living near my house, near my hospital, but they might not be representative. So we cannot extend it to the entire population. That's totally wrong. I think that many people do, even newspapers may be doing actually. They will just go to some supermarket and ask 10 people and then they say, make a big conclusion, or even they catch 100, even if they catch 100 people in front of a supermarket, it is not representative, because those 100 people may be living near that supermarket. Those are 100 people who come to supermarket. So there are many people who may be shopping somewhere else. So a lot of bias. So many of the data Many of the studies done in newspapers, there could be very high bias involved actually. So we need to be very careful. Is it a random sample from the population of interest? Okay, that is also very important. That's why they do studies in different parts in the country. Suppose we want to test a antiviral drug or a vaccine, it has to be done. They call it multi-centric. They may be doing it in 20-30 cities, collecting data, giving the drug, and seeing the results. So you can't just do it in one or two, or just Bombay, Chennai, or Delhi, only 3 or 4. You may have to do 20-25 different cities if you want to get a proper result. So that's very important. Is it representative? Is it a random sample? All these are points which we need to remember when you are doing experiments actually. So unbiased, so many factors determine a good experimental strategy. Am I repeating it sufficiently? Is my results or uniform? Am I randomizing? Is it a representative? And so on actually, okay? So I said there are some controlled variables, uncontrolled variables. So this is somebody delivering a letter, for example, courier. Controlled is what car he is using, how he experience is, how does he know the roads properly, is he a good driver, does he know the locality well? Those are all controllable. But then there is a road blockage, there is a sewage work on the road or VIP crossing. All these are uncontrollable, right? Or too much rain and the whole place is flooded. All these are uncontrollable. So there are controlled variables which you can control. You can always have a very experienced driver. You can have a good vehicle. You have a good route map for him to deliver in fast. Those are all controllable. Like VIP coming or rain, blockage or sewage disturbance are all uncontrollable. So these will always be there in our experimental designs also. So please remember that. So there are something called screening designs. Then there are something called detailed design. That means we do experiments initially with a lot of variables to see which variables are important, which can be discarded, and then take only those and then do a very detailed design. Okay, so suppose I am a chemical engineer. I don't know whether temperature, pressure, pH, RPM, amount of oxygen I am adding, amount of carbon I am adding, amount of nitrogen I am adding, amount of catalyst I am adding. So I may consider many variables and I do a screening, and then I find that only temperature, pressure, and RPM plays important. Remaining 10 variables I don't have to do. So I will do a detailed design only with those 3 variables. So initially I will do with 10 variables, then I will find out that only 3 variables matter. Then I will do a very detailed set of experiments. That's called a detailed design actually. Okay. So in a factorial design, I told you about a drug and diet, fat diet, normal diet, drug, no diet, no drug. Okay, so we can call it high, low. Okay, low is say for example, no drug. High could be drug. Okay, that is factor 1A, drug. B is your diet. Normal diet could be low. High could be fat diet. Okay, so I'm just representing like that. Actually, there are different ways of representing. So if A is your drug, B factor, B is your factor diet. So I have to do 4 experiments, like I said. No, low, high, low, high, low, low, high, low, low, high, high, high. That means I'll take no drug, normal diet, drug, normal diet, no drug, fat diet, drug, fat diet. Okay, so there are, as I said, many ways of representing. I will show you other ways of representing. So for a 2 raised to the power 2 experiments, bottom 2 is levels, top 2 is factors. Okay, these are 2 factors, 2 factors and 2 levels. So I need to do 4 runs actually. Okay, or 4 experiments. Okay, so two levels, two factors. So just like A, B, we can also represent as minus and plus. Okay, two levels, no. -1 means low level, +1 means high level. So like this, sorry, like this, low and high. Low can be -1, high could be +1. Mathematically, it becomes simple to -1 +1, -1 +1. So I have two factors, low level and high level. Low level is -1. So -1, -1, +1, -1, -1 +1, +1, +1. So it could be like low, low, high, low, low, high, high, high. Okay, so 4 different ways of representing.
Professor, we lost your voice. Professor?
So for a 3 factor, just like I said, drug, diet, the third factor could be gender, male, female. Okay, so A could be factor A could be drug or no drug. Factor B could be diet or no, simple diet. C could be gender, male or female. So again, we can have -1 means low, +1 is high. So here 2 raised to the power 3. This 2 represents level, this 3 represents factors. Okay, so we can have -1, -1, -1. That means everything, no drug, normal diet, say male. Okay, then it could, this experiment could be drug, normal diet, male. Okay, you can see all these experiments are in a very random fashion. So there 2 raised to the power 3, I have to do 8 experiments. 2 raised to the power 2, I have to do 4 experiments. Correct. This bottom 2 represents factors, top 2 represents levels. So here we are talking about only 2 levels. It's possible to do 3 levels also. Okay, then that will become different. So you can have 3 raised to the power 2, 3 raised to the power 3, and so on. Actually, so it could be like low, middle, and high. Okay, so when I am doing 2 factors and 2 levels, I do 2 raised to the power 2, 4 experiments. When I am doing 3 factors, 2 levels, it becomes 2 raised to the power 3, 8 experiments. I could have 4 factors. For example, drug, diet, male or female, Asia or Europe. That could be D. Okay, so I could be having D, Asia or Europe. Testing the drug for diet between male and female, between Asia or Europe. That could be factor 4. So it could be 2 raised to the power 4. That means 16 experiments. 2 into 2 into 2 into 2. So Asia we can put -1. Europe we could put +1. So you could have a D column also. Okay, you understand? So this is just a representation, simplified representation in a very mathematical area. Okay, now there is something beautiful about these experimental design. Please look at it. Something very beautiful. Let us take this experiment A, B. Okay, 2 factors, 2 levels, A and B. A represents your drug, B represents your food. Okay, so -1 means no drug, +1 means drug. -1B is low fat, +1 means high fat. Okay, now if you look at these experiments, I just picked up from here, the number of minuses will be equal to number of pluses. Number of minuses will be equal to number of pluses. That means that's called a balanced design. Balanced means whatever I do at high level, I must do equally at low level. So that's called a balanced design. So in any design you make, it should be balanced. Okay, it should not be biased. If I do more experiments at high level, unless that means I am biased, or if I am doing more experiments at low level than high level, that's also not balanced. That means if I give more patients with drugs, that means if I'm doing more ones, that is wrong actually, right? So that's balanced design. Another one is called orthogonality. What is orthogonality? So A, B is there. How do you get AB? Minus into minus is plus. Plus into minus is minus. Minus into plus is minus. Plus into plus is plus. Okay, so I get AB like this. Minus into minus is plus. Plus into minus is minus. Minus into plus is minus. Plus into plus is 1. That's the AB column. Look at the AB column. That is also balanced. Number of pluses equal to number of minuses. That is called orthogonality. So balance is with respect to the main effect. This is main effect A and B. AB is interaction effect. That is A into B. Even A into B also should have balanced. Not only A and B should be balanced, the A into B also should be balanced. That is called orthogonality. So any design should be balanced and orthogonal. Okay. So here, if you look at these three factors, okay, look at the pluses, 1 plus, 1 plus, 1 plus, 1 plus, 4. So 4 minuses. Look at this. All of them have 4 pluses. 4. So that is balanced. Now look at AB. A into B, like I said, minus into minus is plus, plus into minus minus, minus into plus is minus, plus into plus is plus, minus into minus is plus. Like that you make. Look at AB column. There are 4 pluses. This plus, this plus, this plus, this plus. 4 minus. Similarly, AC column. AC column means this into this, minus into minus is plus, like that. AC column, look at 4 pluses here. 4 minuses. So then BC column will be B into C. So you have this into this, plus into minus is minus. BC column also 4 pluses, 4 minus. So this design is both balanced and orthogonal. Okay. So in factorial design, any design you make, you should always have balance and orthogonal. That's very, 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 very important actually. Okay. Now, advantage of this design, we can look at interaction. Okay. So will the drug effect also interact with the type of food I take? So when I look at this column, in fact, that is A into B. A is only drug related. B is only diet related. AB means drug food related. So will the drug effect depends on the type of food I consume. Okay, that is what this column tells us actually. So that's called interaction. AB is nothing but interaction effect. Okay, so I can study not only effect of drug, effect of food, but I can also study will the drug depend on the type of food I take. So if I have a C column also, okay, like in this experiment, I have a C column, which is male and female. I can study will the drug depend on the food I take as well as the gender. So will the drug depend on the food I take? If it is male, will the drug depend on the type of food I take on female? Okay, like that we can study, and that is called interaction. The AB, AC, BC, that's called interaction. In this particular case, we have AB. So when I do a factorial design, we can nicely study both the balanced and orthogonal. So I can look at the effect of main factors A and B. I can also study AB. Okay, that's the advantage. Once I do, then I can do a regression and develop a mathematical equation. You all know what is a regression. I think that somebody else must be doing it. So we can get a linear or non-linear regression relation with the 2 factors. That is the A and B actually. So we can study the interactions here. Okay, A, B. How the drug acts on a person who is taking normal food or a person who is taking fatty food all the time. So the interactions can be seen actually. In this particular case, it's a 2-way interaction. Okay, but you can also have a 3-way. When I am doing a process design, how the temperature will affect the if the pH is different or if the catalyst amount is different. That is called a multi-way interaction. So when we plot the graphs, I'll show you when we plot. Yeah, when we plot graphs. Yeah, when I'm plotting graphs, suppose I'm plotting between temperature versus pH. So I'm taking temperature in x-axis and yield of my product in y-axis. At pH 3.5, I'm getting some graph. At pH 4 point, I'm getting some graph. So this looks very parallel So there is no interaction between temperature and pH. But if I get graphs like this, then obviously, if I'm getting either graphs coming in between each other or going out from each other, that means when I do the reaction at different temperatures, it also pH plays a very important role. Whereas here, pH does not play an important role when I'm changing temperature. But here you can see, depending upon which pH, the graphs are very, very different. And like this. So that means from the graphs, we can say there is an interaction between pH and temperature. Whereas here, we can say that temperature is independently affecting yield, pH is affecting yield independently. So here, we can say temperature is affecting, pH is affecting, but there is also temperature pH interaction to affect my yield. Okay. But there are drawbacks on factorial designs. Like I said, when you have 2 raised to the power 2, you have 4 experiments. 2 raised to the power 3, you have 8 experiments. 2 raised to the power 4, you have 16 experiments. All that's and then it goes up like exponential. Okay, so when I am having 8 variables, I have to do 256 experiments. That's too much, right? So we would like to reduce the number of variables. So the biggest problem with the factorial design is the experiments increases tremendously. So that is why we do something called fractional factorial designs. Okay, fractional, that means you do fraction of a design and you try to get same the information, but you do less number of experiments, because more experiments we do, you all know, it takes time, it consumes chemicals, consumables, cost, everything comes in. So there is something called fractional factorial designs, and that means you do less number of experiments, but you get the same information by doing fractional factorial design. Okay, so there are different types of designs are there. The full factorial design is 2 power 9 n I talked about, but you can also do fractional factorial designs to half of factorial or 1/4 of factorial. That means if I have to do 2 raised to the power 4 will be 2 into 2 into 2 16, but I can do half of 2 raised to the power 4. So that is called fractional factorial design. There is something called Plackett-Berman designs. There is something called Foldover Koshal designs, Latin square designs, Taguchi 2-level designs. There are many designs. They are called all linear designs. Okay, that means there will be only 2 levels. Okay, so that they are 2 levels means linear. But if you have more than 2 levels, that will be non-linear. So these are all 2 raised to the power 2 designs. Okay, so we can have fractional factorial design, Plackett-Berman designs, Foldover designs. So we want to reduce experiments and get the same knowledge, same information. And especially when you are doing with many factors, like I said, experiments may be too much. And I don't want to do too many experiments because it takes a long time. It costs a lot of money also. Okay. Okay, so how do you design a fractional factorial design? Imagine 3 factors like drug, type of food, gender. So I have to do 8 experiments, right? 2 into 2 into 2, that is 2 raised to the power 3. I don't want to do, okay. Now I want to introduce drug, food, gender, but also continent, Asia or Europe. D, factor D. If I introduce that, 2 raised to the power 4 is 16 experiments, right? 2 raised to the power is 2, 2, 2, 2. But I don't want to do that. Can I do only 8 experiments, but I have 4 factors? So there are certain techniques by which we can do. So if you take ABC, this is what I talked about. Then we said AB, we said AC, we said BC. We also said ABC. How do you get ABC? This into this into this. So A into B is minus minus plus, plus into minus minus. Then you see minus minus plus, plus into plus plus. So that is how you get ABC column. So the 8 experiments, but I want to introduce factor D, that is continent, but I don't want to do 16 experiments. So what do? I want to do only 8 experiments. So we call this as a factor D, that is the fourth factor. Okay. So this will be for drug, no drug. This will be for simple diet, high fat diet. This will be for male, female. This will be for continent, Asia or Europe. -1 could be Asia, +1 could be Europe. Okay, so we have 4 factors, but I'm doing only 8 experiments. So that's the trick actually. This is called a half of 2 raised to the power 4 design. Half of 2 raised to the power 4 design. 2 power 4 is a 16 experiments, but I'm doing only half. That means I'm doing only 8 experiments. So the first experiment could be -1, -1, -1, -1, -1. So that means no drug, normal diet, male in Asia. So this could be no drug, normal diet, female, Europe, like that, 8 experiments. The beauty, as I said, is all of them should be balanced design. So here also we can see 4 pluses, 1, 2, 3, 1, 2, 3, 4 pluses, 4 minuses. A also 4 pluses, 4 minuses. So balanced design. So we have achieved a half of 2 raised to the power 4 design. That 4 represents number of factors. Half represents how many fractional I have put. 2, the 2 represents the levels. Okay, half of 2 raised to the power 4. So like that we can do large number of experiments. But when we do fraction factorial design, we will lose some knowledge. When there is a plus, there is always a minus. When we get an advantage, there is always a disadvantage. So there could be some confounding, that is mixing up, or it's called confounding, mixing up. They are also called aliases. Such things can be happening actually. Okay, so there are some variables which get aliased or confounded. So just like I have put D instead of ABC, BCD will be confounded with A, ACD will be confounded with B, and so on actually. So some knowledge is lost when we do that. But you are able to do 8 experiments with 4 factors. So we have cut the experiments by half. So it is a half 2 raised to the power 4 design. Okay. So when we say generally 2k minus q, k is the number of factors, 2 is the number of levels, q represents the aliasing of the factors. So if q is 1, so if you have 2 raised to the power 4 minus 1, that is half fractional. That is, in this experiment, 4 is your factors, A, B, C, D, half is your experiment. Okay, so you have said 2 raised to the power 4 minus 1. So that is like half of 2 raised to the power 4. So, okay, so this will become 8 experiments. Okay, this is how we represent. K is the number of factors, Q represents, Q is 1 means half, Q is 2 means 1/4, and so on actually. So this is called a fractional factorial design actually. Okay, so we can have 2 raised to the power 6, 2 raised to the power 6. If I have to do full factorial, 2 into 2 into 2 into 2 into 2 into 2, 6 times 2, 4, 8, 16, 32, 64 experiments. I don't want to do 64 experiments, but I want to do only 1/4 of 64. 1/4 of 64 is 16 experiments, right? So this is a design giving that actually, because 2 raised to the power 6 alone, 6 factors means 64, but I want to have q as 2, that means 1/4 of 2 raised to the power 6 minus 2, that is 16 experiments what I will be doing actually, instead of 64 experiments. Okay. Okay, so a full factorial design, I am reducing it into either half factorial, I am reducing it into 1/4 factorial, and so on actually. So that's the advantage of a fractional factorial design. Okay, that's the advantage of a fractional factorial design. Okay, I'm able to reduce the experiments. Let me not go too much into this because of want of time. Okay, so instead of a full factorial, I can reduce it and reduce the number of experiments. Like I showed you, 2 raised to the power 4 is 2 into 2 into 2 into 2 4 times. But if I want to do only 8 experiments, I'll do 2 raised to the power 4 minus 1, which is half of 2 raised to the power 4. Okay. So if I have 5 variables, I have to do say 32 experiments. Instead of that, I want to do only 16 experiments. That means minus 1. Okay. So 5 factors, but I'm doing only 16 experiments. I can even do 1/4 of 2 raised to the power 4 also, 5 also. That is 8 experiments. So when you go to 6 factors, I can 6 factors, like I said, 64 experiments. I can do 32 experiments. That is half of 64 experiments, or I can do 1/4 of 64 experiments, or even 1/8 of 64 experiments. But the experiments can be reduced. But there is something called resolution. Resolution also goes down. That means how much accuracy, I mean, how much knowledge I can get also goes down. So we need to strike a balance between how low I can do experiments versus resolution. Generally, they say a resolution 4, you should not go below resolution 4. Okay. 3 resolution is not desired. So if I have 6 parameters, that means instead of doing 64 experiments, you should stop with this type of experimental plan. That means 1/4 of 64 is best. Don't go to 1/8 of 64 because the resolution goes down. Okay. So 1/4 of 64 is okay. 1/8 of 64 is not good. Okay. You can reduce experiments, but don't reduce so much that you lose a lot of information. Okay. So I'm not going too much into the concept of resolution, but as a rule of thumb, it is said that resolution 4 is what is the best. Don't go below that resolution. Okay. So if I take 7 variables, instead of doing 128 experiments, I can go down to 1/4 of that experiment. That is 32 experiments. Don't go below 1/4. Don't go to 1/8 of 132 experiments, because the resolution goes down. So we need to choose designs so that the resolution doesn't go below 1/4. Sorry, 4 resolution 4. This is called a resolution 4 design. Why we are going into fractional factorial? Because full factorial will be too many experiments. That's the main reason, actually. Okay. So there are many designs, like I said. I'm not going to do this. Plackett-Berman design is another approach. So Plackett-Berman design, there are tables available, plus minus tables. So if I have so many variables, say A, B, C, D, E, F, G, I can plan. That is, if there are 7 variables, I can plan 8 experiments. If I have 15 variables, I can plan 16 experiments, like that. So there are designs available, and there are techniques described how to arrive at designs for different variables. So Plackett-Berman design again is also a screening design. So we can develop Plackett-Berman based design. But always remember, all these designs will be balanced. So you can see 4 pluses, always 4 minuses, and so on. So this is called Plackett-Berman design, where we can either generate the design using some techniques, or we can just take a design from a literature for depending upon the number of variables. This is called a Foldover Koshal design. And you can see 10 experiments, 4 variables given here. So these designs are not very, yeah. You may ask why this is minus. This is like a baseline. Okay, so only these are main experiments, 4 pluses, 4 minus. This is called a Koshal design. This is called a Foldover design. So this is like a folding a paper. So when I fold a paper at this place, it's like a mirror image coming here, right? It's called a foldover design. So again, pluses will be matching the minuses. So many types of design. This is called a Latin square design. So I will not go to, I don't have time to go into for 2 factors. Taguchi designs. Taguchi is Yeah, Japanese researcher who did lot of work on these designs. So he has come up with this certain methods by which, depending upon the number of experiments, depending upon the number of factors, how to make a design. So Taguchi has given certain techniques. So we can see, actually, for example, Taguchi's design. This is called L4. That is 4 experiment, number of levels, number of factors. Okay, he has given. These are 16 experiments, 4 factors, number of levels. Okay, so Taguchi has given many designs. This just I am showing 4 variables, 4 experiments. So he has given lot. Again, you can see 8 experiments for number of factors. So he has given strategies for planning the experiments depending upon the number of factors. So this is a okay. 9 experiments. He has even given 3 factors. Just like -1 + 1, he has given -1, 0, +1 also. Like that, So there are many designs which we can follow. This is 16 experiments. He has given for 15 factors. It's a Taguchi design. So a lot of Taguchi designs are given actually. So there are many Foldover, Koshal, Plackett, Berman, Taguchi, full factorial, fractional factorial. These are designs available, and they are all called linear designs because you have plus and minus. Once you bring in 0 also, that means 3 levels, then they are not linear designs. They become non-linear designs. Okay. So let me touch briefly about non-linear designs also. Just like -1 + 1, we also have 0. That means 3 levels. Or you can have more than +1 also. So five levels also we can consider. So these are called non-linear designs. Okay, there are in non-linear designs, there are something called box Benkan design. Then we have called central composite design, CCD, and then central composite design and 3K factorial designs. Just like 2 raised to the power n, we can say 3 raised to the power n. So these 3 raised to the power n factorial designs will be too many experiments, right? So suppose if I have 3 raised to the power factor 2, you may have to do 9 experiments. If I do 3 raised to the power factor 3, 27 experiments. Whereas when you go to central composite design, the number of experiments will be much less when compared to full factorial designs. Okay, so 3 raised to the power 3 will be 27 experiments, whereas with central composite design, you may have to do only 15 experiments. Okay, so this is called a box Benkan design. Like I said, you will also have 0, just like +1 and -1 will also have 0. That is another level. Okay. This is a box Benkan design. This is for more variables, 4 variables, 5 variables box Benkan designs. Then this is central composite design for 3 variables, ABC. CCD is central composite design. And so on, actually, so we can have 3 raised to the power k, just like if you remember 2 raised to the power k type of designs, box Benkan design, central composite design, full factorial designs, 3 raised to the power k. Here fractional factorial, 3 raised to the power k minus q. These are called second order designs because we have more than 2 levels. So we can develop non-linear relation. When we have 2 levels, you can develop only linear relation, right? 2 levels means we can develop only linear relation. But if you want to do x square, y equal to ax square plus bx plus c, then those are called non-linear relations. So we have to have values at 3 levels. Whereas if I am developing y equal to ax plus b, I have to do experiments at 2 levels, right? In a regression, if you remember your regression, actually. So these are called non-linear designs, which can be used where you determine the variables at least 3 levels or 4 levels or 5 levels, unlike 2-level designs, which are called linear designs. So in 2-level designs, we had full factorial, fractional factorial, Koshal, Foldover, Taguchi, and then in non-linear designs, that is 3-level designs, we have full factorial 3-level, we have fractional factorial 3-level, we have box Benkan, we can have central composite designs. So all these are useful if I'm going to develop non-linear mathematical model. If I'm developing linear mathematical models, I will have 2-level type of designs. Okay. So these are some examples. Very quickly, I covered both the screening designs as well as non-linear designs, but one needs to spend much longer time if one is interested actually. Okay. I will stop with this, and if there are any questions, I'll be pleased to answer the audience.
Thank you, Professor Mukesh. The session is open for discussion.
Yeah, any questions?
Students, if you have any questions, you can ask Professor. Any doubts?
Anybody has any doubts? You can ask on the linear designs as well as non-linear designs. Or you can type in the chat box also. I have the chat box open. You can type in the chat box.
Any questions? No? No more questions. And I would like to thank Professor Mukesh for joining us today and elaborating, so giving an overview of the experimental designs that can be followed, both the linear and non-linear methods that can be very useful in constructing their experiments and generating data for analysis. I hope this session will be useful for all the students participating in this work. Thank you once again, Professor Mukesh, for joining us. Thank you so much.
Thank you very much. Thank you. Thank you.